At this point, you are probably sick of me saying machine learning is nothing but a geometry problem. But here's where it gets really important. The question we want to answer right now is, why are neural networks so important? Why can't we just use a single neuron? I mean, it seems to be a pretty good model. It's nice and interpretable. Large weights means the corresponding input is important, and very small or zero weights mean the input is not important. Unfortunately, this type of model only gets us so far. You'll recall that when we discussed linear regression and logistic regression, I said there are two different ways we can make things more complicated. The first way we can make things more complicated is to add multiple inputs. That's something we encountered already. This is still pretty simplistic because you can always picture a plane in your head, a straight, non-curving surface that separates data between classes. The second way we can make things more complicated is that the decision boundary or regression function we are looking for is not a straight line or plane. This is what we are interested in when we discuss neural networks. The reason the equation W transpose X plus B equals 0 gives us a hyperplane is because this is the actual definition of a hyperplane. There's no way around this. There's no possible setting of W and B that could give you a curved surface. So how can we get a curved surface so that we can solve more complicated problems? One method you might have thought of is to use feature engineering. For example, let's take linear regression. Suppose that for whatever reason, salary is proportional to the square of the years of experience, or put another way, that salary is a quadratic function of years of experience. Then we could say that y hat equals to ax squared plus bx plus c. Believe it or not, this is still just linear regression in disguise. It's easy to see this by doing the following. Take x, the years of experience, and call that the input feature x1. Then take x squared, the years of experience squared, and call that the input feature x2. Then my y hat becomes an equation of the form y hat equals w1x1 plus w2x2 plus b. Of course, we've already learned that this is just linear regression. The problem with feature engineering is that there are many different possible features. Squaring the inputs is common, but so is combining the inputs. So if I have the inputs x1 and x2, then I could make one of the features x1 times x2. We call these interaction terms. But what happens if I have three input features? Now I have to consider x1 squared, x2 squared, and x3 squared. But we also have to consider x1, x2, x1, x3, and x2, x3. In total, there are 6 quadratic terms. As an exercise, you might want to list out all the possible combinations we could have if we had 4 inputs or 5 inputs. You should discover that the number of terms we have to consider grows quite fast, and thus feature engineering, even in this simple form, seems to be a somewhat clumsy solution. But now, let's remember our neuron. If we consider just the first layer of a neural network, we can see that there are multiple neurons. Importantly, they are all multiple different neurons. Each neuron is a different nonlinear feature derived from all the inputs. Because we've applied the sigmoid activation function, the feature is not just a simple linear combination of the input features. So you can think of these as feature 1, feature 2, feature 3, all the way up to feature m. Now, a lot of people wonder, how does this make a neural network nonlinear? Remember that a linear function always takes the form W transpose X plus B. Our neural network takes the form of the equation you see here for a 2-layer neural network. This is what we get if we drop the z term and just make the whole thing into one equation. W2 transpose sigmoid of W1 transpose X plus B1 and then plus B2. The important thing to notice about this is you cannot simplify this into a linear function. If you could, then we would have a linear decision boundary. So let's see what would happen if we had no sigmoids at all. Let's suppose we have a regression network with no sigmoid. Then it's just W2 transpose times W1 transpose X plus B1 plus B2. Of course, using basic arithmetic, we can expand the product due to the fact that there's no sigmoid. It's just straightforward multiplication. Then we just get W prime transpose X plus B prime, where I've substituted W prime equals W2 transpose times W1 transpose, and B prime equals W2 transpose times B1 plus B2. And so you can see that if we have no sigmoids, this just reduces to a linear equation. There is an added bonus to using neurons for our features. If you recall, all the weights and biases are randomly initialized and found using an iterative algorithm called gradient descent when we call the model.fit function. What this means is that instead of having to do manual feature engineering to try and guess what features might be good, a neural network will do this automatically. In the olden days of machine learning, feature engineering, at times, used to be the only method of really applying machine learning successfully. And usually this would require domain knowledge. So if you wanted to build a good image classifier for, say, lung cancer detection, you would have to be very knowledgeable about different computer vision techniques. But not only that, you would also have to be very good at looking at X-rays of lung cancer. By the way, note that I'm not a doctor, so I don't know if they actually look at X-rays, but you get the idea. If you wanted to build a good stock predictor, you would have to be very knowledgeable about finance. If you wanted to build a good fraud detector, you would have to be very knowledgeable about the insurance industry. And as you may have heard, deep learning is so popular because it allows people who are not domain experts to build very good machine learning models. Nowadays, we have people who are not expert radiologists building state-of-the-art image classifiers for medical diagnosis. All they are experts in is machine learning itself. That is pretty powerful. One tool I really like is the TensorFlow Playground. You can find it at playground.tensorflow.org. Basically, this lets you train a neural network on some synthetic data right in your browser. It lets you see for yourself that the neural network is learning a nonlinear decision boundary. So if you go there, it looks like the default is the donut problem, where you have one circle inside another circle, and of course the decision boundary should be a circle. Your inputs are only the raw data, x1 and x2, but you could also use feature engineering if you so choose. So you could select x1 squared, x2 squared, x1, x2, and even the sign of x1 and x2. But we're not going to do that because we want to show that neural networks are able to learn nonlinear features using only the original inputs. So you never have to manually create things like this yourself. And so by default, we have a 2 hidden layer neural network with 4 hidden units. So there's 1, 2, 3, 4. So let's just run this and see what happens. All right, so as you can see, it learns the nonlinear decision boundary quite efficiently without the need for any manual feature engineering. You're encouraged to play around with this yourself. So try switching data sets. So you can pick, let's say, this one, and then run it again. Also, try different numbers of hidden layers and different numbers of units per hidden layer. This should help give you a stronger intuition for how neural networks work and lets you observe for yourself that they are finding nonlinear decision boundaries.